Okay, great. So if you have any question, you can paste them on the chat, and there's also a Zulip chat that you can find next to the program. So without further ado, let's introduce Ramesh. So we are very happy to finally have Ramesh on the schedule. I had the chance to meet Ramesh actually last year. He doesn't need a lot of introduction. Actually, he's a professor at MIT, and he's also the head of MIT Media Lab of Camera Culture Research. And his work is very versatile, actually. He has done a lot of work in computer vision, computational health, sensors, imaging, and he's also into privacy preserving contact tracing very recently. He has this initiative on PathCheck. And he also actually works on machine learning. And today he's gonna talk to us about split learning. So Ramesh, you can go ahead.
Excellent. Thank you, Antigone, and thank you for the organizers for inviting me. I'm going to talk a little bit about how we can think about distributed machine learning that borrows ideas from various fields and apply it to kind of the current crisis of COVID-19. And I want to emphasize this notion of an API, because often distributed machine learning is not suitable for an API aspect of it, for this orchestration. So I'm going to emphasize a little bit more on that part. So, let's take an analysis of how to deal with a crisis. So if you think about a hurricane versus pandemics, hurricanes are about, satellite view and prior models, and it's kind of a top-down solution. But epidemics are innocent people infecting other innocent people. And so we need a bottom-up solution by treating individuals themselves as sensors and emitters. And that's where smartphones come in. And I think that's why it's an exciting area for us, because we can imagine, all kinds of interesting distributed machine learning algorithm that preserve privacy using techniques that we're talking about in this workshop. So everybody knows about exposure notification, which is how to use smartphones to detect proximity, notify if somebody has crossed path, do some self-assessment, and still create some kind of a global knowledge. Although the data is siloed in everybody's cell phones, still create a global knowledge for public health and businesses to understand at like a dashboard level what's going on. So actually in the current crisis, it's not clear at all how we can achieve privacy and the global view at the same time. So as Antigone said, one of the reasons I got into this, into applying distributed machine learning methods to the pandemic, is we launched a spin-off from MIT called PathCheck Foundation, and we're helping many states and nations launch their exposure notification and case management apps. And we already have 5 states and territories in the US, some European countries and others. And it's become world's largest, open source nonprofit project. So if you have a lot of research ideas, algorithmic ideas, please join the open source movement here. So we can bring them to the masses, because hundreds of millions of people will be using these apps. And we have been fortunate with pretty good philanthropic funding to hire a full-fledged software engineering team, in addition to epidemiologists and so on. And so this is kind of the app and the dashboard. And then we use different proximity APIs. Right now we're focusing purely on Apple, Google, Bluetooth APIs, but you can imagine over time we can include others as well. So the reason why this problem is interesting is it's not just about exposure notification, but it's also about triage and testing and quarantine and exit and so on. And I know some people on this call actually went through this experience personally. This is a very complex process, and public health is very broken. We believe in confidentiality, but not anonymity or privacy. So this whole process is very siloed, and you have to give up everything about yourself, which means that people who are marginalized or undocumented, or if you're a tourist in another country, you don't want to trust the local government. This system is broken, right? And same thing with businesses. So the goal for PathCheck is how do we achieve this using privacy preserving API at every stage, exposure notification, triage, testing, quarantine, and so on. And this is a graph many of you have seen, kind of the trade-off between privacy and utility. For Google Maps, we willingly give away our GPS coordinates So we get fantastic utility of where the traffic is, but for health data, we don't. And that's why dealing with pandemics like this is very, very challenging. And our hope is that we can achieve both simultaneously. So we have written a bunch of papers in this space, encrypted GPS, encrypted Wi-Fi. Antigone is a co-author on a couple of these papers. It's just a very rich area for exploration. So if you're interested at all in using ideas from crypto, kind of the topic for this workshop, in a very fast-moving deployment area, please ping us. We are putting out everything in real time, source code, papers, even before we think about which journal to send it to, we put it out on archive to stimulate a conversation. So just email me, and this is the GitHub page for it as well. So let's talk specifically about the idea of split learning. And we know about the small data problem of distributed machine learning. It's siloed, how do we train the algorithms? And the reason why the data is siloed is it could be because of quality and talent to actually make the data usable. But often the middle one, which is privacy, regulation, and trade secrets, makes it impossible to share the data between different organizations. And even if you do all of that, what's the incentive? You should do it. And the common reason is, let's do it for science, let's do it for social good. But that's not good enough. I think the market forces should be making that happen. So in our group at MIT, we have invented 3 different methods. We were the first one to publish a paper in meta learning in AutoML, one of the very highly cited papers in this field from our group. And then split learning, which I'm going to talk about today, and also notions of data market, of how market forces could actually improve add some grease and make it function as a more liquid markets. And as I said, if you think about health data, kind of the user devices lead to privacy, which could be a wearable, which could be a phone, and so on. Hospital, they cannot share because of regulations like HIPAA and so on. And if you have a research tool like a data bank or a biobank, then they may not want to put it out there. Imagine a pharma company that wants to actually help the world, but not give away trade secrets. How do you do that? So all these reasons make it critical to think about these mechanisms. So again, going back to privacy versus utility, if you make it confidential, that's not privacy. You can anonymize it, but as you know, that's not sufficient protection because of overlapping data sets. You can obfuscate by adding noise with differential privacy. And then probably the best solution is to use homomorphic encryption. But then on the utility axis, maybe all you can do with encryption is some analytics and statistics. But if you want to do full-fledged inference or train machine learning models, then these techniques are not very suitable for that, differential privacy or homomorphic encryption. So 2 techniques have emerged. And if you think about COVID-19, right, it's not just about exposure notification, but there could be questionnaires. What are your symptoms? Did you travel? What are your existing health conditions? Or were you wearing a mask or not? Did you have a sense of smell or not? And maybe if we start using the phones to listen to your cough or take a picture of your wound or things like that, or your gait. So there may be a lot of information locked away on individuals' phones, and we would like to build extremely sophisticated machine learning models in real time, in matter of days, as opposed to signing legal agreements between the Chinese and the Koreans and Italians and here in the US. So how can we do that in near real time? And that's kind of our mission for PathCheck. So the 2 ideas here, some of you know about federated learning, and then the group from the technique from our group is called split learning. And the idea behind both of them is don't share the raw data, but share the wisdom, right? And by doing that, we can protect the privacy of the raw data, but still make it available for either inference or training. So if you have to do, let's say we want to create a master algorithm to detect for pneumonia or treatments from chest x-rays or treatment plans, then one idea would be some kind of a collective intelligence, right? Instead of us getting data from those hundreds of locations, I might send an intern, medical intern, to go to all those places to say, can you go and learn that information and then come back with your wisdom in my conference room? And then I'm going to show you a new chest x-ray to see if any one of you or a group of you can help me figure out whether this has this COVID-19 symptoms or not, right? And that would be one way of preserving privacy, and that's exactly how federated learning works. You train a partial model at every phone or edge device, and you do an averaging. Of course, there are epochs and so on. That's a secondary detail, but the idea is it's a collective wisdom. Split learning, on the other hand, I like to use the analogy of elephant and the blind people, where somebody might say, "Hey, I feel this feels like a wall, with this kind of a texture," or somebody might say, "This feels like a rope with this length and this particular characteristics." And basically, what the blind people are doing, they're converting the elephant into a feature vector, right? Without taking a picture of the elephant. Of course, we don't care about the privacy of the elephant in this case, but if they wanted to preserve privacy of the elephant and still convey what it is, they will still convert that into a feature vector. And that's what split learning is all about. You can again use the analogy of the interns, and they're going to convert their medical records, in this case, the chest X-ray, and just send notes. They're going to convert the chest X-ray into a few notes. There's some cloudiness, there's some pigmentation, and so on, and they'll send those notes to the master AI. In this case, maybe the first one is diabetic, the second one is elderly, the third one has different ethnicity. So all of them have slightly different features for that particular demographic. And despite this extremely heterogeneous data sample, we can still make it happen. And to be slightly more precise, we're going to take a deep neural network and we're going to split it. The early layers will execute at the client and the later layers execute at the server. And at the client, we're going to convert the raw data into a smashed wisdom. And that smashed wisdom is what's going to get sent to the server during inference or during training. And the benefit of this method is, you get significant gains over SDG or a federated learning methods, because clearly you're converting raw data into a few bytes, as opposed to sending models that could be tens of megabytes, right? So we get this rapid benefits. And also, despite heterogeneity, this works really well because when you're converting each data point into a feature vector, you don't really have to worry about heterogeneity or mismatch in sample size or anything like that. So you get this automatic benefits of as if you're on a single machine. So far it's good in terms of compute and bandwidth. And let me come and talk a little bit about other challenges. So when you think about federated learning, if you have very low compute and communication, then you cannot really send large models. Think about speech recognition. You simply cannot send a gigabyte model onto a small phone or a wearable or a medical device, right? So you would like to clearly convert, in this case, your speech signal into a feature vector. On the right side, if it's health data, then you're not going to have millions of phones, but you might have only 5 or 10 clients, and it's going to be naturally not homogeneous. But the models themselves will be pretty complex because it's not a highly optimized model. So again, federated learning is not a good solution because it's sending things back and forth. And maybe the most important point to make here is that split learning can behave like an API. Think of it as JPEG, think of it as about encryption, where one party can convert the raw data into smash wisdom. Think of it as an encrypted signal, and some other party at some other time can pick it up and use it. As opposed to federated learning, where all parties have to be together, synchronized at the same time, and they all have to trust each other, right? Because the entity that's orchestrating the federated learning has to activate the server, has to tell the client to wake up and start converting his data, send it back, wake up other clients. There's all this orchestration that's taking place that's completely eliminated in split learning. It truly becomes an API model where there's data that's encrypted or compressed or smashed, and it's sent to the server. Server can do anything it wants, or use it or not use it, willing to pay for it, and so on. So this API way of thinking about it is going to create a lot of innovation because it encourages third-party developers to work on it, as opposed to federated learning, where one entity has to coordinate everything that's going on. So we think there are some real benefits to that. And I'll leave this slide up during Q&A, which is other challenges when it comes to compute, data, communication, and machine learning. Whether it's too little data or non-ID data or vertical partitioning as opposed to horizontal or incremental updates, ownership and control of the whole ecosystem. These are all the issues that you would have to deal with in federated learning that goes away to some extent in split learning. So to conclude, this API way of thinking about smashing, encryption, compression can go a long way, whether you're thinking at the device level or the organization level or at the biobank level, and would love to collaborate and work with many of you as we tackle this COVID-19 challenge to take some of these ideas out. But in terms of research, I think this may be the era for us to really deliver it to tens of millions of people. Thank you.
Thanks a lot, Ramesh. That was great. As the questions are coming, I would like to ask you if you can talk a little bit more about like the idea of smashing the data in split learning. Yeah, how is it different from the federated learning so that we get to know a little bit more?
Yeah, thank you. This was not planned, but I have some extra slides. And so, you want to convert your raw data into the smash data, let's call it X to Z, while maintaining the utility. So, you can have your traditional loss function on the right side, which is Y and Yn, but then we have to add this extra term, which is distance correlation. So we want to make sure that Z does not reveal, because Z is being sent to the server. So we want to make sure Z does not reveal much about X, but Z is still useful for inference or training, right? So in this sense, it's very different from federated learning, because in federated learning, you're sending the model weights up and down, and here you're sending the feature vectors up and down. It's just that the feature vectors are constructed in such a way that the feature vectors don't reveal something about X, or at least doesn't reveal the feature that you care about. So if I take a picture of you right now, whether you're a man, or your gender, your expressions, your identity should not be revealed, but maybe it's okay to reveal your a particular attribute, for example, right? So let's say we don't want to protect expression, but we want to protect your identity, your gender, your race, and all those things. So only the expression kind of goes forward, but everything else is whitened out. So that's why it's very different than federated learning, because in federated learning, the notion is that I'm just going to send you the wisdom, which is another great way of protecting privacy. It's just that when it comes to communication, bandwidth, and speed of convergence, we get a lot of benefits here.
Yeah, can you say a little bit more on how we can achieve this compression?
Yeah, so in a typical neural network, you already have the representation learning that's supposed to be compact compared to the raw data. In case of computer vision, X-rays, and so on, you might have a 10 megapixel image, but the representation could be just few kilobytes. Could be even 1 kilobyte. So you get this 10,000 times compression of the data, but also naturally you get a privacy or protection at least, because you cannot go from this 1,000 kilobytes back to the original X-ray. Okay, I'm going to say that and also kind of contradict myself, which is if you have a really good representation learning, then in fact, 1,000 bytes is good enough to represent every X-ray, just X-ray that's out there. So if you think about the distance correlation, we notice that in a traditional, in traditional ResNet or PKFA or network, you would have a distance correlation of 98%, 0.98. And that's why we have to use these techniques that reduces the distance correlation. And then with our technique, we can go back to about 0.2 or something like that, while taking a very minimal hit in the utility as well. So the compression in terms of number of bytes is natural. Compression in terms of kind of information theoretic sense of it, you have to be careful, because you might want to throw away the meaningless information that you're carrying with you for what the label is. If the label in case of human faces was just expression, I should be able to throw away everything else that I'm carrying with it.
Thanks, got it. I have one more question. So now if you go back to your slide about the issues that split learning helps solve where the federated learning doesn't.
Right.
So can you talk a little bit about this? For
Sure.
example,
So yeah, so I mean, I had things in red, which are, and there are challenges with distributed learning anyway, right? Which is, what if there are unreliable nodes and there are adversarial clients, which is on the left side on compute? What if there's unethical use? Is there a local compute versus, a server compute? And bandwidth, there's limited communication, there's latency, there's dynamic. These are all issues that any distributed computing system would face, whether it's federated or split learning. But when you come on the right side, you start seeing these issues with, what if you have too little data? What if every client has exactly one data point? Let's say it's 1,000 bytes. Would you send a 10 megabyte model of federated learning? Let's say it's your wristwatch and all it's sending you is an ECG signal, right? Why would you send a 10 megabyte model up and down to every watch when that every device has only one data point to contribute? And this is where split learning has a lot of benefits. Of what if your data is very unbalanced, right? On one node, maybe you have one data point. On the other node, you have 1,000 data points. You shouldn't have to worry about it. If you take, if the number of data points is even smaller than a batch size, then clearly there's nothing you can do with with traditional machine learning, with federated learning. So that becomes a challenge. Vertical partitioning is another example where, if one entity has, radiology data, the other entity has the pathology data, the third entity has some social data, then putting them together is going to be challenging because in federated learning, you would need all three of them at the same node to train it. Otherwise, the weights will be. But here, because we're focusing on feature vectors or representation learning, we can convert the pathology data into its representation and just send it up. We can take the radiology data, convert the representation, send it up, and so on. So you get this natural a natural kind of exploration of your feature space without worrying about the model. The problem with thinking of the model as your wisdom is that you need the whole model to be updated. So and so on. And the other challenges are exposing labels. So if it's self-labeled, then that's great. But what if labels are not private, and so on. Another big challenge with federated learning is that what about you have incremental updates, right? Because in case of split learning, the wisdom really stays with the server. So if there's an incremental update from one of the nodes, then what you would have to do in federated learning is for that particular node, you have to send the whole model, let that node update with its own batch size and update that whole network and put it back in. In case of split learning, that doesn't really matter because node can wake up, after a few days, after everybody else has finished and converged, and say, hey, you know what? I have a few thousand extra data points. Do you want them? And the server takes them, and server can do a judgment. It can train its part of the model, the upper layers of the model, with and without this contribution, and say, if it changes a lot, it's probably not good data. It's outside my distribution anyway. Or say, actually, not. It seems like, according to whatever metric I have, this is actually useful data that I can use, and you can do an incremental update, and you can immediately get going. If there's in case of autocorrect, which is a classic example in federated learning, if one particular, in LA, if one particular artist like Cardi B is suddenly very popular, Cardi B will show up for autocorrect, and the whole model can be updated, and you don't have to worry about taking very same sample size. Like Hammers take same number of people from New York and LA and Houston to make sure my model is representative. I don't have a problem with that because I can just take several people from LA and I'm ready to go to update my model. So given that the server has plenty of power, plenty of influence in providing an updated model, actually makes this more suitable for an API-based version, API-based mindset.
And also, sorry, I need to ask something more. Also, I guess in that case, if some parties have less data, so you are exposing this information, right? Because you want to achieve.
Say that one more time.
Sorry, I was saying if different clients have different amount of data, then you are leaking who has more data, right?
Mm-hmm.
So I guess if you want to hide this information, then you will need to send more data over the channel, right? So you are losing some properties of this matching.
Yeah, that's right. You're right. So if you have a single data point, then you might start exposing a little bit more than usual. So there's some privacy in a larger batch size. That's what you mean, right?
Yeah, yeah.
Yeah, that's very true. So you could, but I think the benefit of split learning is that unlike federated learning, where if it's a near linear model, you could imagine, your gradient updates themselves could reveal, something about the data point. That's not true here. So if you have like a 10 megabyte, 10 megabyte model in federated learning, the gradient updates themselves are roughly 10 megabytes. That's not the situation here. Here, the amount of data you're sending out, you might have a 10 megapixel X-ray, but what you send out is only 1,000 bytes. So the 1,000 bytes mathematically can be guaranteed to not reveal much about being able to reconstruct the original X-ray or the original human face. So the challenge with small data or even one data point is not the same as what you would imagine in gradient updates in federated learning. Is that, did I make a point?
Yeah, I got it. Okay, so maybe I should set up. Let's see if there are more questions from the audience. If not, I can keep asking you a lot of questions on the topic. It's very interesting. But yeah, let's see if there are more questions. Let's wait a bit to see. Oh, somebody's putting a question on the chat. Let me check. Yeah, actually, can you also paste the question in this chat? I don't have open the Zulip chat. Actually, I lost it. Yeah, can you please paste the question also here?
I can speak the question. I would just want to see the GitHub link again.
Oh, I see. Okay. Okay, there's a question. So Ramesh, what's your view on the fragmented and different approaches to solving these problems and the likelihood that they will converge sufficiently and soon for problems like contact tracing?
Let me understand the question one more time. What's your view on fragment and different ways to solving these problems? And then, okay, I'm not sure whether it means machine learning or exposure notifications in general. So let me just answer both. So I think if in terms of exposure notification using Bluetooth versus GPS versus QR code, I think there's a lot of fragmentation. So the approach we have taken at the PathCheck Foundation, which is a spin-off from MIT, is that being very inclusive and creating a GitHub code base that supports all these features. Right now, we're focusing on the Google Apple protocol, Bluetooth protocol, just because many states are going to use that because Apple and Google are behind it. But we'll continue to support everything else as well. But maybe the more interesting question for this workshop is how do we get machine learning as part of COVID-19 apps? And this is really an exciting area for us. And we would love to invite you to come join us. Just send me an email at raskar@mit.edu. And we would love to start kind of a discussion group that meets once a week in what we can do for machine learning for COVID-19 apps. So you can imagine, using the phone sensors, sucking up data from your health records in a privacy-preserving way, and using data streams that are coming from other places like social media data, even environmental data, and so on. So there's a whole bunch of things we can do in this space that's very, very exciting. But again, fragmentation can only be avoided one base, and hopefully some standards around them. I think the other question on, can split learning be used to perform privacy preserving training for CNN models? That's exactly the point. So we are not using encryption in this case specifically, but there's a notion of privacy using distance correlation. So in fact, it is, I mean, that's the whole idea, that we want to use split learning for privacy preserving DNNs or CNNs for that matter. So again, if you have a convolutional layers right in the beginning, as you know, several early layers will not protect privacy, and you can still reconstruct from any of the cut layers or the activations. But we design the Z in such a way that if you don't if you don't do anything, then the Z, the cut layer, will actually reveal something about X. But as I said, we use this distance correlation trick to reduce the information content in Z, which still has sufficient utility or small hit in utility, but very high privacy. There's another question here, if I can just read. So designing Z without disclosing privacy attributes of X and kind of queries we design is going to be a very important aspect. Then smashing comes in. Is that right? So absolutely right, Abhilash, which is the two main things to take out of this, my talk, is one is that there's yet another way to do distributed private machine learning, which is by thinking about converting data into feature vectors as opposed to sending models themselves. And second is, how do you create a feature vector so that it doesn't disclose specific attributes of X? I think your question was, is it sequential? No, it's together. You train the network in such a way that it preserves utility to create Z. At the same time, it reduces, it improves privacy of those attributes. So the training takes care of both because the cost function is modified. The utility and privacy cost function are put together.
Got it. I think it's a combination of designing the data attributes using something like zero knowledge proof and multi-party compute, but on top of it, run the algorithm part of it, because it is more, Z seems more towards the zero knowledge part of things, and then building AI on top of zero knowledge.
So just to be sure, we work in ZKF and MPC in other areas, but this particular talk had no notion of secret multi-party computation or anything like that. It's just clients, servers, and you don't need any coordination. They can collude if they want. There's no such problem as such. So this particular talk I just did has nothing to do with zero knowledge proof or secret multi-party computation. It's very similar to federated learning, distributed machine learning, where you have hundreds or even millions of nodes and you have one server.
Got it. But the way you design Z, where we are ensuring that only, let us say, pseudonymous representation or something of data in such a way that it does not provide the privacy sensitive data of the user information, but at the same time include enough amount of variables or the attributes of the variable which can be shared, from which the intelligence can be explored or the wisdom can be explored, and which is shared as a feature vector for the upper layer.
Yes, but I mean that's part of the training process. So we are not doing anything. It's almost black box, because we just set the cost function, and automatically we get out a Z that has these beautiful properties. So that's why I'm saying that it doesn't have, we don't have to it's not hand tuned, it's not handcrafted. We don't say, like the analogy I gave you of a human face, maybe you want to transfer the expression, but not gender or race or things like that. We don't really have a knob called gender or race or expression, right? We just say, hey, this is the utility I want, and I'm going to just suppress everything else, right? So that's why I don't want to think of it as like particular feature attribute or something like that. It's happening almost in a black box manner.
Correct. Is there a standard way of doing this across data? Because this approach would be different for different kinds of data.
Yeah, the beauty is that because we are staying within the kind of the framework of a typical CNN or DNN, we are not inventing any new terminology here. It's just cost functions. We're just taking deep neural network and so on. So that's why whether using an X-ray or a speech or human face data, it doesn't really matter because the idea is the same, and we don't have to do anything special in terms of that. So if you look at some of the libraries that have been published by us and also by OpenMind for split learning, you'll see that kind of pretty broadly available. And a lot of people have done benchmark studies. Many research groups are working on split learning now. So they have all published their papers and their code base as well. So kind of interesting to see what different applications people are using.
Got it. Thanks. Very interesting.
Excellent. I need to sign off as well.
Sorry. So we have more questions for you. Don't go away.
Okay. I need to sign off in a couple of minutes because
yes. We have 2 minutes more. Can you talk a little bit about malicious security? Many people are asking about malicious security. So you can see the question in the chat.
Yeah. I think malicious client is a big problem for any distributed machine learning. We have not solved this problem. We haven't studied this problem that well yet because, so we have this problem called, MRMR, kind of minimally relevant, minimally redundant, maximally relevant. And I think those are very difficult problems to solve. So how do you know that the feature vectors that are coming at you are actually useful and they won't take you out of your distribution and so on. So, instead of sending a chest X-ray, maybe you just send me ultrasound data. I don't know what to do with it. It could screw up my training altogether, right? So there could be just intentional misinformation or unintentional corruption of that data as well. And then if you are really malicious, then of course you could collude and convert seemingly heterogeneous data into some kind of a bias amongst clients. So we have not studied the topic in great detail.
Great.
But
okay.
It's a great area for exploration.
Great. So we can get one last question. Actually, this one is about the vaccine. So not about the vaccine. So it's about the contact tracing. So there's a recent poll found that 35% of Americans will not accept the FDA-approved vaccine.
Right.
This raises the question of whether machine learning can be used to predict the effectiveness of contact tracing and vaccination in the face of an adversarial population.
Yeah,
So,
thank you for asking that question, because without getting into the politics of vaccines, this notion that, if all the test sites, all the hospitals can suddenly start sharing the data, we should be able to create global models, in the beginning, just analytics, but over time for full-fledged machine learning, is the reason why we are in it, right? Exposure notification is just the beginning. So I think this is just a rich area of exploration. Like, how do we encourage all the hospitals, all test sites to give us their data so that we can, in fact, start talking about, not just analytics, but even predictions in this space. Excellent. Thank you very much for hosting me, and such a wonderful platform. All the best.
thanks a lot, Ramesh.
Thank you.
Thank you very much.
And you can contact Ramesh offline if you have more questions.
Yeah, just email me at rasker@mit.edu. And I'll write the smartlearning.github.io. Thank you.
Bye.
Thank you. Bye. So we next have 4 contributor talks. First talk is of CryptoFlow 2, Practical Two-Party Secure Inference, and it will be given by Divya Gupta. Divya?
Yes, hi everyone. I think Ramesh needs to stop sharing his screen perhaps. Or should I just go ahead and share my screen?
Yes, try actually.
Yes, okay, let me try that. Okay. Yes, you're able to see my slides, right?
Yes.
Okay, great. Okay, thank you for having me here. I'm very excited to talk about a very recent work, which is CryptoFlow 2, Practical Two-Party Secure Inference. This work will appear at ACM CCS this year, and is a joint work with Deevashwer, Mayank, Nishant Kumar, Nishant Chandran, Aseem Rastogi, and Rahul Sharma, all the folks from MSR India. Okay, so the focus of this talk is secure machine learning inference, and let me begin with a motivating scenario. Consider a hospital who has some pre-trained machine learning model for some disease prediction. And on the other hand, you have Bob, who has his medical report and wants to learn the diagnosis on his report based on this machine learning model. What makes the situation tricky is that the hospital considers his ML model as intellectual property, plus it has been trained on sensitive patient data and hence cannot be given in the clear to Bob. Bob also deems his medical report as sensitive and does not want to give it to some arbitrary hospital who claims to have some machine learning model. So the question is, can these two parties perform machine learning inference collaboratively without revealing anything but the output? So in this special case, the hospital should learn nothing, and Bob alone should learn the diagnosis of his medical report. This problem is a special case of general secure multi-party computation, which has been very well studied in cryptography for more than 40 years. In fact, the special problem of secure machine learning inference has also gained a lot of attention in the in crypto and security communities, starting with the work of CryptoNets, followed by Secure ML, Minion, Gazelle, Delphi, and many others. But the issue is that all of these works suffer from two major drawbacks, which limit their practical applicability. The first drawback is that computing ReLU functions securely is quite expensive. So ReLU of X is defined as maximum of X and 0. And this is in fact the most commonly used activation function in deep neural networks. Of course, you can compute this with garbled circuits, but they have very high communication cost. The other drawback is erroneous computation of fixed point arithmetic. So all the works on secure inference assume that the underlying machine learning model has been expressed as fixed point arithmetic. This gives a nice ring structure for the cryptography to work, and we generally don't want to work with floating point as that is quite inefficient. And now, preserving inference accuracy requires faithful implementation of this fixed point arithmetic. For example, fixed point multiplication requires you to do integer multiplication followed by some truncation or right shift operation of a secret value. Again, this can be done with garbled circuits, but is quite expensive. So many of the prior work sacrifice correctness of this fixed point operation and do what is known as local truncation. The issue with local truncation is that the result can probabilistically diverge from clear text in random and unpredictable ways. And even when you have small errors, they can accumulate over large computation, for example, in DNNs. So all in all, this not only leads to loss in prediction accuracy, but also breaks correctness of standard MPC, and hence is highly undesirable. So in this work, we resolve these two drawbacks, and here are the technical results. First, we give an efficient protocol for comparison or the millionaires problem. We built on this protocol to give an efficient protocol for what is known as DReLU, which is 1 for positive X and 0 otherwise. And we use this to build efficient protocols for all the nonlinear layers, say ReLU, MaxPool, ArgMax, etc. Then as next technical result, we give new mathematical theorems to express division of a secret value by a publicly known divisor over arithmetic shares. And then we give efficient protocols for division and truncation, which is a special case of division by power of 2. Using these protocols, we are able to give faithful implementations of fixed point matrix multiplications and convolutions. These are called the linear layers of the DNN, and also average pool, which uses division by public value. For each of these functions, we give protocols for both L-bit integers, say 32-bit integers, and also general rings, which includes the case of prime fields. Once we have these protocols, we build a framework called CryptFlow2, which has two types of secure and correct inference protocols. The first one is PSI-OT. Here, the linear layers, which are the matrix multiplications and convolutions, are evaluated using oblivious transfer, and the arithmetic happens over L-bit integers. In PSI-HE, the linear layers are evaluated using additively homomorphic encryption scheme, and it works over prime fields. What I would like to emphasize is that all our secure protocols are bitwise equivalent to clear text. Next, as an example, I would like to compare our ReLU protocol against garble circuits, which is the one used by all prior works. In this scenario, we want to compute ReLU on a secret value, which is arithmetically shared between two parties, say P0 and P1. So P0 has X0, P1 has X1, and you want to compute ReLU of X0 plus X1. And here's a comparison with garble circuits. Here we compare for both the case of L-bit integers as well as general rings, both as a function of bit length as well as for 32-bit integers and prime fields of 32 bits. So as you can see, for general L-bit integers, we are more than 7x better and 11x better for the general rings. And for the specific case of 32 bits, we are almost 10x and 14x better respectively. Okay, so once we have these great protocols to evaluate them at scale for realistic machine learning tasks, we integrate Psi as a backend to Cryptflow, which is a work by the same team published at IEEE Security and Privacy earlier this year. So at a high level, Cryptflow starts from native TensorFlow inference code, and at a push of a button does crypto and compiler magic and automatically gives out secure inference protocols. In the case of Cryptflow, the backend used was Porthos, which is a three-party secure inference protocol. In this work, we integrate PsiOT and PsiHE as additional backends to Cryptflow. And with this system, we show that we outperform prior 2 PC works in both latency and scale by an order of magnitude. So first, I will compare with prior work in terms of latency. And for this, we considered two benchmarks considered in Delphi, which is the state of the art prior to our work. The two benchmarks are a CNN from Minion for CIFAR 10 and ResNet 32 for CIFAR 100. And here's the comparison. So for both of these benchmarks, we know the time and communication split between linear and nonlinear layers for Delphi. And as you can see, for both of these benchmarks, the time and communication is dominated by the nonlinear layers. Next, we replace the nonlinear layers of Delphi with our new protocols. And with this, we see more than an order of improvement for both time and communication for both of these benchmarks. Next, we evaluate our protocols on ImageNet scale benchmarks. Here, we take the three benchmarks, SqueezeNet, ResNet 50, and DenseNet 121, which are the same benchmarks considered in Cryptflow work. And this gives us the first ever evaluation in 2PC of ImageNet scale benchmarks. Just to give you an idea how big these benchmarks are, the largest benchmark in our case, which is ResNet 50, has 25 million parameters compared to only 0.4 million in the largest benchmark of Delphi. Moreover, for each of these benchmarks, our fixed point code matches the prediction accuracy of TensorFlow. And our secure protocols are bitwise equivalent to clear text, so our secure protocols match the prediction accuracy of TensorFlow. For each of these benchmarks, we evaluated them using both PsiOT and PsiHE in both LAN and WAN settings. And we observe that for LAN setting, we can run within 10 minutes, and for WAN, we run within 20 minutes. So finally, I would like to summarize by saying that we give a practical two-party inference protocols, which are bitwise equivalent to clear text. For this, we give efficient protocols for comparison and DReLU, and also give new theorems and efficient protocols for faithful truncation and division. Finally, we build a system called Cryptflow 2, which automatically compiles from TensorFlow inference code to two-party secure computation protocols with support for both OT and HE for linear layers, which is multiplications. And with this, we outperform prior works in both latency and scale by at least an order of magnitude. So our paper has been submitted to ePrint, should be online soon, and implementation is available on GitHub.
Thank you.
That's all.
We have time for 1 minute for questions. I see one question on the chat. The security is only semi-honest. It seems
Yes.
you use OT or...
Yes, yeah,
It seems
sorry, I forgot to mention it. It's only semi-honest and not malicious.
Okay, Antigone has a question. Antigone, you can go ahead. You are on mute, Antigone.
Sorry. Divya, thanks a lot for the talk. Can you give a quick insight on why your new protocols outperform the previous ones? A few words about the technique.
About the technique also. Okay, so at the heart of it, we have a new milliners protocol, which is just for comparison. So the way it works is that, okay. So in Gabel circuits, you pay a multiplicative cost in the security parameter, right? So I have a slide. You're able to see the slide, right?
Yes.
Yes. Okay. So in Gabel circuits, you pay a cost of 4 lambda L for the comparison. In our case, what we do is we build a new protocol for comparison, which at a high level does the following. If you have to compare two integers x and y, it is same as comparing the upper bits of x and upper bits of y, followed by, if they are equal, you compare the lower bits of x and y. So you can write this recursion, which breaks this problem into like from L bit integers to L by 2 bit integers. We have to do comparisons and equality for both of these. So we built on this recursion. This is the naive protocol. This has bad communication complexity. Then we do a bunch of optimizations on this basic protocol, use some tricks from K choose one OT on bit strings and so on to get the communication cost down to lambda L instead of 4 lambda L, which is for Gabel circuits. Does that answer your question at a high level? I don't know how to.
Yeah, I see. It's 2-party, right? It's not 3 parties.
No, it's 2-party. It's
yeah.
2-party. Everything is 2-party. Yes. 2-party, 1 corruption,
Okay.
semi-honest.
Okay, thank you, Divya. We'll continue to the next speaker, which is Carsten. Carsten will talk about fairness in the eyes of the data, certifying machine learning models.
Can you hear me? Fantastic, and I think the slides should also be visible. Good, then let's get started. So yeah, I'm going to talk about certifying machine learning models, in particular certifying their fairness. And this is joint work together with Shahar Segal, who's from Tel Aviv University, Chaya Ganesh, who's at IIS in Bangalore, if I remember correctly, and Benny Pinkas, Yossi Keshet, and Yossi Adi from Bar-Ilan University. And I'd also like to use this opportunity to thank the organizers of the workshop for putting together such a nice workshop. The problem that we're tackling in this work is the problem of fairness. So fairness in general is well known to be somewhat difficult to handle. For example, take this situation where you have two people who are asking a insurance company for an insurance, and the first person, for example, gets an acceptance from the insurance company, and the second one will be rejected. And the only difference of these two people would be, in this case, their color, one of them being blue, the other one being green, and there's nothing else different between these two. So this is somewhat inherent that this is unequal treatment or unfair treatment of two kinds of people. This generalizes to the setting where we have computers, in particular machine learning models that we use to make predictions, meaning that if we are now in a server-client setting, what we try to avoid is to have an algorithm, a machine learning algorithm, which for different clients that are otherwise being equal, make different predictions that are non-explainable with the underlying data, right? So we want to avoid that we are in a situation where there is a server and there's a client and different clients get treated unfairly. So this has been subject to quite some research in the past few years that led to some interesting results. And the setting that we consider is the following. We have, as mentioned, the client. The client wants that its input X is going to be classified in a fair way by a machine learning model M. And on top of that, we also want that this input X is being kept secret. On the other hand, our techniques also apply, as can be seen, as we show in our work, that without this input X having to be secret. And on the server side, we have that the model owner wants to keep the model M secret. While at the same time, we assume that the model owner might act maliciously. meaning that the model owner might generate a model that treats people unfairly, and it does actually ignore, let's say, best practices in training models that are fair. So this this means we depart from where, for example, previous work has been done, where people have been considering a, let's say, semi-honest setting with an honest server that just tries to make a model that is fair and get some help on the outside. And instead, we're considering a setting where there's an unfair server and we want to force it to make fair predictions. In our situation, we introduce a so-called regulator to make this possible. There, the intuition is that if we would, at every invocation between a client and the server, make a test that a model is fair, then this test would probably be expensive, right? So we want to kind of push it to a, let's say, pre-processing phase or to some other phase where a model gets certified. And we also think that you know, a client might not have the necessary expertise to figure out if a model is fair or not, right? I mean, we're right now in a situation where it's already difficult to argue if certain models are fair. In particular, an end user of, for example, an insurance will not be in the situation to find it out. So we want that this can be done in the pre-processing phase. Actually, we're not the first to consider the situation. This idea of using a regulator that signs a model and you know, thereby says that a model is fair has been used in some previous work called blind justice, but in a different setting. And yeah, so the idea on a very high level is to have an interactive test between a server and the regulator that's going to use MPC to test a model in a black box way. And then the regulator is going to sign the server's model if and only if it considers the model as fair. And then later on, the server and the client can use this certificate on a model to figure out if you know, if the model was changed in between. So this implicitly gives us a guarantee that this thing is fair, right? So now the obvious question is, how do we find out if a model is fair or not? As I said, we're not enforcing a training phase that leads to a fair model. So that means that we need a verification algorithm that finds out if a model is fair or not. And our algorithm so our situation can be seen as follows. So we assume that there's, let's say, the server and the regulator. Let's assume this server is being evil, and both of them have access to a certain distribution D. Now, what the server is going to do, it's going to interact with this distribution D. It's going to sample values from this distribution. It's then going to generate a model. And we have actually no guarantees whatsoever about what is in this model. Now, all we actually allow the regulator to do in this situation is to interact with this distribution, and then the regulator is actually going to send queries to this model and is going to get, for example, labels based on these inputs. And it's going to do that repeatedly, let's say m times. And in the end, they're going to say yes or no if the model is, according to the regulator's definition, fair or not. And yeah, and this, what we actually show in our work is some kind of PEG style guarantee for a model. So what we would show is that if a test with a model M passes for a regulator, then what the regulator guarantees, for example, is that the model's predictions over all groups, the probability that a model's predictions over all groups differ by more than epsilon is less than delta, right? This is like one of these standard PEG style definitions. So now there are two ways one could set it up, right? The first way would be saying, okay, I have a regulator that has arbitrary access to this distribution. It's just always going to sample stuff and it's going to interrogate the model, and at some point it's going to say, yeah, everything is fine or not. Right? This is basically just testing if a model is following the same distribution as you would expect it to. So there's no surprise that you can prove that if you have enough samples, you know, you can verify something about it. So there's not much. So we call this the private data setting, because the regulator has a lot of private data from this distribution. Right? So this is not the interesting part. The interesting thing that we do is that we also say, what happens if the regulator has a test set T, which is sampled according to this distribution, but this test set is actually known to the adversary, right? So in this situation, what you would assume is that the adversary could, so you would first set up the test set T and some other parameters, and then the server can generate a model afterwards. And obviously what you would assume is, well, if you just, overfit on the test set T, then, they shouldn't be able to get many guarantees out of this. But and we argue that this is actually a more realistic setting, because in reality, there, like for a lot of tasks, there's only like 2 or 3 data sets that you have out there. And, collecting new data sets is expensive. So you can't just walk around and, just make up new data. So this might be a worst case assumption, but it's not so worst case after all. So how do we deal with this situation? What we actually do is we randomize the input data. We randomize the test data that is being used. And the intuition is, well, if the model is robust on inputs with noise, then it generalizes well. And if it generalizes well, you would hope that it's fair. And it's actually something that is quite standard in the machine learning community for other reasons, where you would re-randomize your training data to use less training data, or to make your model robust to changes. And actually, for example, for images, you could use noise, you could use scaling, you could use cropping. These are like different ways of randomizing your test data. And what we actually show is that the fairness of a model is correlated to how robust a model is to this randomization, and we empirically validate this. So for more details, as my time is almost up, so we're hopefully going to soon put this work on archive, and obviously if you're interested, I can give you a preprint, and we're curious to see how to implement all these details with all the MPC in practice, and if this can be extended to other fairness notions. So we only consider specific fairness notions, and there are different ones around there. Arguably, we might not take the best ones for certain situations, so it would be interesting if this work can be generalized to other situations as well. And with this, I'd like to thank you.
Thank you, Carsten. We have no time for questions. If there will be any questions, we'll take them at the end of the session. I want to proceed with Avital. She's going to talk on.
Yes, some slide. I hope you can see it.
Oriented neural architecture design.
Yes.
Right.
Okay, so Okay, so my name is Avital Shafran. I'm a PhD student from the Hebrew University of Jerusalem, and I will be presenting our work, Script-Oriented Neural Architecture Design, which was done together with Gil Segev, Shmuel, Peleg, and Yedid. So neural networks have been a revolution for many applications that do not have practical or standard algorithmic solutions, such as medical diagnosis and various computer vision tasks. But at the same time, the use of neural networks also presents 2 conflicting privacy concerns. There is the issue of the privacy of the data, and there is also the issue of the sensitivity of the model itself, as has been previously mentioned. And those 2 privacy concerns may limit or slow down the practical use of neural networks in sensitive domains such as healthcare, for example. So one promising approach to solve this problem is by using secure computation. You can think about this as a 2-party computation problem, where we have the client with data X and the service provider with a neural network N, where we would like to modify the neural network N to operate on encrypted or encoded data using techniques from secure computation, mainly homomorphic encryption, garbled circuits, or secret sharing. And the way this is done in practice is in a layer-by-layer conversion method. We take advantage of the sequential nature of neural networks, which are usually built as a composition of layers, and we convert each layer into a privacy-preserving layer, so that given a new private input, we sequentially compute the composition of those private layers over the private input to reveal an output that only the client, the data owner, can decrypt or decode to reveal the actual result. The problem is that in general, secure computation may be significantly slower than regular computation, or might require much higher networking bandwidth, especially if we use garbled circuits, for example. And this may limit the use of privacy-preserving neural networks to only simple, shallow architectures. And you cannot really apply those methods to modern deep neural networks. So there's been an extensive effort in the community to optimize the cryptographic protocols used for those conversions. And we propose a complementary approach. Design new neural network architectures that are crypto-oriented and already have the limitations of secure computation in mind. So the motivation for this comes from the fact that in regular neural networks, linear layers such as convolutions and nonlinear layers such as ReLU or max pooling have pretty much the same computational cost. So regular optimizations of neural networks usually focus on minimizing the number of linear computations. While in secure computation, this is not the case. As we all know, nonlinear computations are very expensive. To demonstrate this, we took 3 efficient neural network architectures, SqueezeNet, ShafranNet, and MobileNet, and we measured the difference in runtime between the original architecture and the same architecture after we removed all activation layers. So on the left side, we can see that in the non-secure setting, this results with only less than 10% runtime reduction. While on the right side, in the secure computation setting, we can see that removing all ReLU activations from the architecture results with more than 60% runtime reduction. So our method suggests to reduce the number of nonlinear activations. We propose to do so using a novel activation layer, which we call partial activation layers. And this layer takes the input to an activation layer and splits it into 2 branches with different ratios. In this example, it's a 50-50 ratio, but we can select any ratio we want. We then apply the nonlinear activation on one branch only, and then concatenate the results. This enables us to maintain the nonlinear nature of the neural network, which is very important, while at the same time reduce the number of nonlinear computations. It's worth mentioning that we do this on the architecture before training it. So in the training process, the model learns which information should flow through the linear channel branch and which information should flow through the nonlinear branch. In addition to that, we also suggest to completely remove activation layers that make no significant impact over the accuracy, and to choose nonlinear variants that have lower resource requirements. For example, the popular ReLU activation has many other variants. One of them is the ReLU 6 activation, which clips the values between 0 and 6, and has many benefits in the training process. But when computing in a secure manner, ReLU 6 activation costs twice as much as the regular ReLU activation, as it is composed of 2 comparisons. So if this has no significant impact over the accuracy, we suggest avoiding using such expensive variants. Some related work, so concurrently to us came out Delphi, and recently came out 2 other works. All of them rely on neural architectural search algorithms to address this problem, and their method is different than ours. So I would like to demonstrate now how we apply our method on the MobileNet architecture, which is a modern, efficient neural network. And this architecture is built using a repeating building block, which is very common in neural networks, in modern neural networks, where this block is composed of 3 convolution layers, where the first 2 are followed by a ReLU 6 activation, and the last one is linear. So as we have mentioned before, we avoid using expensive variants such as ReLU 6, so we completely replace it with a ReLU activation. We also found out that we can completely remove the first ReLU activation from this block throughout the network without having a significant impact over the accuracy, and replace the second ReLU activation with a 50% partial activation ratio. All of those modifications gives us an improvement of 79% in communication complexity and 63% in round complexity, with only a minor accuracy loss of 1% for CIFAR 10 and 2% for CIFAR 100. In addition to that, we also experimented with the MNIST and Fashion MNIST datasets, where on these datasets we are able to even use a 25% partial activation ratio, and this gives us an even better improvement of 83% in communication complexity, and basically no accuracy loss at all. So this is a summary of our results. We experimented with 4 datasets, CIFAR 10, CIFAR 100, MNIST and Fashion MNIST, and 3 efficient neural network architectures, SqueezeNet, ShafranNet, and MobileNet, which we have just discussed. And on all of those architectures, on all of those experiments, we are able to significantly improve the communication and round complexity with having a minor or even no accuracy loss at all. So to conclude, our goal was to improve the efficiency of privacy-preserving neural network inference. We suggest to do so by reducing the number of nonlinear computations, for example, the radio activation, which gives us a substantial speed up with only a minor accuracy loss. To do so, we also propose a novel activation layer, which we call partial activation layers, that enables us to remove most of the radio activation or all of the radio activation or any other activation function that we want in the model. And using our method, we are able to achieve significant improvement over various state-of-the-art neural networks. Thank you.
Thank you, Avital. We have one question on the chat. How do you decide which activation layers have no significant impact on accuracy?
Okay, so we did this handcraftedly. We experimented with removing different activation layers, and we found out which one does not have a significant impact. Another method would be to do this in using neural architecture search algorithms or any other algorithm to let the model itself find which ratio we want in the partial activation ratio. As we can think about completely removing activation layers as a 0% partial activation ratio.
Another question on the chat, I think it's very related. How do you decide how much accuracy loss is okay?
So there's a trade-off between accuracy and efficiency. You can decide that you care more about accuracy at the cost of having lower efficiency. So you would select a higher ratio in the partial activation ratio. You can select a 75% and get almost the same accuracy. It depends on the exact implementation and the exact problem, but we found that 50% on most problems is a fair trade-off. It's pretty much fair between the efficiency and the accuracy.
There's another question from Hussein. Using which framework you see 60% runtime reduction between normal and secure one?
So we used the secure and then framework using the implementation of the TF encrypted library.
I see. There is also a question about if you can share the paper, if there is a preprint.
Yes, so the paper is on archive, and I will just send the link in a minute.
Okay, just write it in the chat. Okay, I think anyone has any other question? So we'll take Avital, and we'll continue with Rita. Going to talk on privacy preserving decision tree training and prediction.
Okay. Hi, can I share the slides? Yeah. To share screen. Okay. Can you see my slides? Is it okay? Yeah. Yeah?
Yes.
Okay, perfect. So just a second. Okay, good. So hi, my name is Margarita. I'll be presenting privacy preserving decision tree training and prediction. This is a joint work with the Diakavia, Max Leibovich, Chezi Reshev, Roiron, and Moni Shahar. And this work is going to appear in ECML PKDD this year. So I want to start with explaining how data is treated in our days in companies. This work is motivated by the architecture and the company use cases. So in companies, we have a huge centralized storage called the data lake, where all the data of the company is stored. And we have multiple applications ingesting data to the data lake. And so the data is going to be first encrypted and then stored in the data lake. On the other hand, we have also many applications like machine learning models and analytics that are going to use this data for computation. So the data is going to be decrypted and given to the machine learning model, for example. And so the situation is that we have lots of applications, and each one of them is accessing lots of data, actually. So this situation is quite problematic because it's enough for a malicious attacker to break into only one of these applications to get a full access to the whole data lake and the whole data of the company. So we want to solve this problem by having data always encrypted. In particular, we want to modify the machine learning models to fully operate over encrypted data without having any access to the clear text data and without having any ability to decrypt the data at any point of time. So by doing that, we will be able to reduce the attack surface, of course. And I want to fix first few notations for the rest of my talk. So I want to call the applications that are ingesting data to the data lake a client, and the machine that is hosting a model or training a model, I want to call it a server. And the privacy goals that we want to achieve is that the server learns nothing on the input data or the computation result, and the client should learn nothing other than the computation result. In particular, the model should be remain private. Okay, so in this work, we're going to focus on decision trees and also models that are using decision trees as a building block. And what we show is decision tree prediction and training over encrypted data. We have provable privacy guarantees, and I won't discuss the privacy in this talk, but I can say that we have privacy against under standard assumptions, CPA, encryption, we have privacy semi-honest, and if we assume circuit privacy for the training, we can get malicious. Okay. Okay, for prediction, we have a non-interactive protocol with running time approximately 1 second, and in this 1 second, we can do few thousands of predictions in a batch. And for training, we have a lightweight protocol between a client and a server, where the client time and the communication complexity is independent of the dataset size. And I want just to say that the dataset size is actually the heavy component in the training procedure. Okay, so the server will be linear in the dataset size, and the running time varies from minutes to hours, again, depending on the dataset size. And I want briefly compare it to prior works. So for prediction, prior works had interactive protocols for prediction with communication complexity proportional to the tree size or the tree depth. And in training, prior works considered an MPC setting where multiple parties are jointly communicating and training a model, where each one of them holding a portion of the data set in the clear. And this is very different from our setting. We don't have any entity holding the data in clear text, and we're training the model over encrypted data. Okay, good. So I will start with prediction. And in this work, we're considering, of course, prediction and training over data encrypted with fully homomorphic encryption. So I want just to mention what is fully homomorphic encryption. So it and secure encryption with additional property of homomorphism with respect to addition and multiplication. So I can add 2 ciphertext to get a new ciphertext, and that will decrypt to the sum of the values. And the same is for multiplication. And just to notice that this allows me to do polynomials, this property. Okay, and so I want to start with explaining how prediction looks like in the classical setting over clear text, just that we can go from here to the encrypted setting. So we have a tree where each node have a threshold and index of a feature, and we're getting an input, a sample of k features. Okay, and we're going to traverse from the root to the leaf, where in each internal node, we're going to compare the value of the feature with the threshold of this node. Okay, and if the evaluation is 1, we're going to go right. Otherwise, we're going to go left until we reach a leaf. So basically what we're doing, we're evaluating a threshold function at each internal node. This is the procedure. And equivalent formulation of this procedure is by this formula, where we assign to each path in the tree a value according to the evaluations of the threshold function along this path times the value of the leaf, and we sum over all these values. Okay, and because only the correct path of the input in the tree will be evaluated to 1 and the rest will be evaluated to 0, we will be left with the correct prediction, with the leaf value, the correct leaf value. Okay, good. So I want to examine what we need to do in order to evaluate it over encrypted input. So now we're given encrypted sample of k encrypted features, and in each internal node, we first need to figure out how we evaluate the threshold function over encrypted input. And this we need to take care of, but once we have it, we can just plug it into the formula, and because the formula is consists of additions and multiplications, we can homomorphically evaluate it and get an encryption of the prediction result. So basically the problem of prediction over encrypted data reduces to the problem of evaluating a threshold function over encrypted inputs. Okay, so in this work, our approach is, instead of using the threshold function, we're going to use a low degree polynomial approximation for the threshold function. And this is different from prior works that consider interactive protocols. Okay, so let me just remind you how to get a low degree polynomial approximation of the threshold function. You need to fix a degree d and an interval, and then to find a polynomial of degree up to d that is closest to the threshold function within this interval. Okay, so here we can see an example of L2 norm closeness by L2 mean square error, what called, and degree 16 between -2 and 2. But in our work, we noticed that for decision trees, actually not all errors are of equal importance. And in particular, errors that are close to the threshold are less significant than errors that are far from the threshold. Okay, I less care to be error if I'm close to the threshold. If it's a bit smaller or a bit bigger than the threshold, it's not that a big deal. Okay, so what we're going to do in this work, we are approximating with weights. We put weights along the interval to actually to signify where the error I care and less care. And basically what we're doing is we solving this optimization problem in the bottom of the slide. Okay, so we can see the difference. Now this is the same interval, L2 norm, degree 16 approximation, but we can see that the function is much smoother, but the slope is a little bit bigger. Okay, and this is what I have to say about the prediction. For training, I won't go into details at all. I will just say that we use also the weighted low degree polynomial approximation combined with other techniques to get the training. Okay, and I want just to briefly mention the experimental result. We implemented the training over encrypted data and tested it on UCI standard data sets, ranging from small to big ones. So you can see for small, we get like 19 minutes for training, and for big ones, about 20 hours. And we use the single core machine. So all of these can be parallelized and get further improvements in the running time. Okay, and for accuracy, we again tested it on UCI standard data sets, and we get accuracy very, like, some of the data sets we perform better, some we perform a little bit less, but approximately the same as the classical one. So I want to conclude. We get our result is a privacy preserving decision tree prediction and training. We have high accuracy. Our client is lightweight in the training, and in the prediction we're non-interactive at all. We have a practical training running time, and also for prediction we have promising prediction time. So I want just to say that this is the first, as far as we are aware of, practical training of trees over encrypted data, like in terms of running time. Our main tool is a low degree polynomial approximation of the threshold function that might be also useful for other applications over encrypted data. And our protocols can be extended to work also over encrypted trees and random forest, and we can do also boosted trees for prediction. Thank you. That's it for me.
Thank you. There are some questions in the chat, but I think we don't really have time. So we'll take it offline, and we have a break now for 30 minutes.
Okay.
We'll continue with 2 more invited talks of Ilya Mironov and Shafi Goldbus. So thank you, everyone. Thank you, all the speakers. And we'll see you in 30 minutes.